Now we're getting into some common coordination numbers that you will observe when you look at coordination chemistry. Coordination number 4 gives two different possibilities for its arrangement of ligands around the central metal cation. First is the square planar complexes. So, for example, if you have a D8 or D9 cation, so D8 cations are plus 2 cations like Ni, Pd, Pt, and some D9 cations like Cu2+, they will form square planar compounds. And actually there's many of them that are very well known. For example, I'm going to ask you to look up Bosca's complex. You could just type in Bosca's complex and it'll tell you why it's important if you want to Google search it, and Wilkinson's catalyst. So there are some out there, okay? Now, tetrahedral complexes are the other type of coordination compound that has a coordination number of 4. In main group metals, like tellurium 4+, you can get this distorted tetrahedral, or what we've called seesaw configuration, in certain compounds. So this is an example of one right here. Now, tetrahedral complexes generally contain either D0, D5, or D10 metal cations. So for example, nickel with a small ligand like carbon monoxide can form this tetrahedral complex right here, NiCO4. So here's what you need to remember about the last two slides. You need to remember that coordination number 4, those are square planar complexes, and they generally form from transition metal cations that have a D8 electron configuration and possibly a D9. However, tetrahedral complexes generally form with transition metal cations that have a D0, D5, or D10 electron count. A little more on coordination number 4. Geometric isomerism is very, very common in square planar compounds. As a matter of fact, there's a ton of them out there. However, chirality is very rare. It's hard to do, and I think it takes a non-symmetric polydentate ligand to do that. However, due to the way the ligands are arranged in tetrahedral compounds, you don't see geometric isomers. However, there are a number of chiral compounds that can be observed, and you will find them if you look in the literature. Coordination number 5 has two common conformations, trigonal bipyramidal and square pyramidal, and one very odd form, which is this pentagonal planar. You can imagine, put something like a ZE atom, write that down, and then at the corners of a pentagon, write the 5 fluorine atoms. And that's how it's coordinated. It's planar. It's weird. However, there's a small energetic difference between trigonal planar, or trigonal bipyramidal, and square planar. So this leads to a very important idea called fluxionality. Fluxionality is the rapid interconversion of a coordination 5, a compound with a coordination number of 5, into two very similar geometries, and it happens over small time scales. As a matter of fact, it happens so fast that NMR cannot distinguish the difference between between the trigonal, bipyramidal, and square pyramidal forms of a compound. Now there is a mechanism behind fluxionality. So let's say, now this is a commonly known coordination compound, pentacarbonyl iron 0, okay? Now notice that you've got 3 carbonyls on the equatorial positions and 2 carbonyls on the axial positions. What happens is these 2 carbonyls right here can bend back, and all of a sudden when you do that, you now have 4 carbonyls in about the same plane, but it's all below the iron atom, and 1 carbonyl that's just sticking way out there. What can happen is this carbonyl and this carbonyl that are pointing behind the page and in front of the page can move up. Here's your new plane. It looks kind of trigonal bipyramidal or trigonal pyramidal, and when these 2 move up, it reforms the trigonal bipyramid. In coordination compounds with coordination number of 5, NMR cannot distinguish between the axial and equatorial positions. Coordination number 6 is the most common coordination number. It's seen in a lot of compounds, and you've seen me draw it a ton of times in the lecture slides. It's octahedral geometry. As a matter of fact, all transition metal cations are known to form octahedral complexes, and I'm showing just an example of 2 of them right here. There is another coordination number. It's called trigonal prismatic. I think there's a picture in your textbook, but it's very rare.